In today's video, we're going to be talking about what a solution to a differential equation is and how to check if a given function is a solution to a given differential equation. Then we're going to talk about a graphical representation of some differential equations called a slope field, what solutions to differential equations look like on that slope field. Now, a note that will be applicable to us for our entire class. Yesterday, we saw examples of some differential equations which contained partial derivatives. For example, the Maxwell-Faraday equation contained a partial derivative with respect to time. So did that equation for conservation of mass for fluid dynamics. But in this class, we are not even going to be considering differential equations which contain a partial derivative. That's a much more advanced class. There are courses, generally speaking, at the graduate level which focus exclusively on that, and we're not going to cover it. We are going to be studying what's called an ordinary differential equation, which contains not partial derivatives, but the regular derivatives from Calculus 1. Ordinary differential equations are called ODEs for short. So, all differential equations in this class are going to be ODEs. Yesterday we discussed that a solution to a differential equation was a function which, when substituted into the equation, resulted in a true statement. For example, let's go back to this equation which had the form y prime was equal to some constant multiple times y itself. This, for example, is very similar to the differential equation arising from short-term exponential population growth. Let's determine whether the function given by y equals e to the power 2x is a solution to this ODE. First, let's calculate y prime and figure out what that would be equal to. That's a simple chain rule calculation, 2e times 2x. So let's plug that in for y prime on the left side. Meanwhile, on the right side, we have 2 times y, 2 times e to the 2x. So this statement is true. Yes, 2e to the 2x is equal to itself. And therefore, yes, y equals e to the 2x would be an example of a solution to this particular ordinary differential equation. Let's try it again here. In this case, we have the function y is equal to cosine of 2t plus 3 times sine of 2t. Let's determine whether or not this is a solution to the ODE y double prime plus 4 times y equals 0. So first, let's figure out what y double prime would be equal to for this particular function. Y single prime, the first derivative, would be equal to negative 2 sine 2t plus 6 cosine 2t, and y double prime would be equal to negative 4 cosine 2t minus 12 sine 2t. So let's replace the y double prime in the differential equation with this expression. And then let's replace the y with the given formula y equals cos 2t plus 3 sine 2t. Let's check and see if that actually does equal 0. But when I distribute, I'll get a plus 4 cos 2t, which will cancel with this negative 4 cos 2t. I'll get a plus 12 sine 2t, which cancels with this minus 12 sine 2t. And so after simplification, we get 0 equals 0, which is a true statement. And therefore, I would say yes, y is solution to this ODE. I'm going to say this once now, and I'm going to say it again because it's important. When someone gives you a function and asks you to check if it's a solution to a differential equation, you do not have to solve the differential equation. You do not have to try to find the solutions to the differential equation. That's hard. All you need to do is plug this function into the differential equation and see if the result is a true statement or not. Let's vary it up a little bit. In this exercise, they want us to find values of r for which the function e to the rt is a solution of the following differential equation: y double prime minus 5y prime minus 6 times y is equal to 0. Now, in order for this function to be a solution to this ODE, I need to be able to plug that function into this equation and get a true statement. So let's figure out what y double prime and what y prime would be, and then let's plug y prime into this equation, see what happens. If I take the first derivative of e to the rt, then by chain rule I get r times e to the rt. And y double prime will just bring down a second factor of r. So now let's plug that information into this equation. Y double prime was r squared e to the rt, minus 5 times y prime, which is r e to the rt, minus 6 times y, which is e to the rt, and that has got to be equal to 0. So have a look at this equation now. All three of these terms contain an e to the rt. E to the rt is never 0. So it's completely safe to divide both sides of the equation by e to the rt. And when I do this, what's left? What's left is the r squared from the first term, the 5r from the second term, the negative 6 from the final term. After simplification, if I'm saying that y equals e to the rt is a solution, then the inevitable consequence is that the r must satisfy this equation. So let's solve this by factoring. I think minus 6 and plus 1 will do. So r could be equal to positive 6, or r could be equal to negative 1. These two values of r will correspond to a function which is a solution to this equation. In other words, two solutions to the ODE are given by y equals e to the 6t, where r is equal to 6, and y equals e to the minus t, where r is equal to negative 1. If r is equal to 6 or minus 1, then r is a solution to this equation, which means that our function is a solution to the original ODE. Again, I emphasize, checking to see if a given function is a solution is a completely manageable and easy problem. Usually, you can answer that question using just the techniques of Calculus 1. Take the first derivative and or the second derivative, plug those into the ODE, and see if you get a true statement. Checking if a function is a solution is a fundamentally different act than finding a solution from scratch. This is generally pretty difficult. And even that is much easier than actually solving the differential equation, which is finding every solution to the differential equation. This is, generally speaking, very hard, and in certain situations actually completely impossible, even with modern technology. So don't make the problem any harder than it needs to be. If someone gives you a function and just wants you to check if that function is a solution, don't make your life harder by trying to solve the equation yourself. Now, as we've noted, actually finding a solution to an ODE from scratch can be a little bit difficult. But in certain special situations, it's possible to actually construct the graph of a solution to an ODE, even if you don't know the actual formula for the solution. So when can we use this technique? When can we graph solutions, even if we don't know the formula for a solution to an ODE? We can do this when we have an ODE of the form y single prime equals some expression containing just x's and y's. So this ODE contains only a first derivative. It doesn't contain any second derivatives or third derivatives, etc. And we have something like y prime equals some expression containing x's and y's on the right side. In this situation, the idea that we're going to use is that geometrically, the derivative of a function, y prime, is equal to the slope of a tangent line to the graph. For example, when we had the simple function y equals x squared, and we calculated y prime equals 2x, if you plug in x equals 1 to this function, you get 2, which is the slope of a line tangent to the function at that location. So the idea that we're going to use to sketch the graph of a solution, even without knowing what the formula is we're going to calculate the value of y prime at various locations, then we're going to draw tiny tangent line segments whose slope is equal to the value of y prime at that location. And then we're going to, in some sense, string together those tangent line segments to construct a sketch of the graph of the solution. So what we're going to try and do is we're going to try and build some tangent line segments, maybe something that looks like this at various points, and then we're going to smoothly connect those line segments to try and sketch the solution, the function y. So this brings us to a graphical object called a slope field, also sometimes called a direction field. A slope field is a graphical representation of an ODE of the form y prime equals f of xy. And here's how you construct the slope field. You pick a location on the xy plane. Let's just call it xy. Plug the location xy into your ODE to find the value of y prime at that location. And then sketch a tiny line segment with slope y prime at the location x, y. Let's sketch a rough slope field corresponding to the ODE y prime is equal to x minus y. Then, even though it's not possible at this moment for us to solve this ODE, let's use the slope field to sketch the graph of a few possible solutions to this ODE, a couple of different functions that would make this equation true. So slope fields are graphed on the xy plane. And I'm just going to pick a random position. Maybe I'm going to pick the position 0, 0. So now I'm going to take that location 0, 0, and I'm going to plug it into my ODE to figure out what the value of y prime would be at that location. So x equals 0, y equals 0, 0 minus 0 is just 0. So now I'm going to draw a tiny line segment with slope 0 through the location 0, 0 at the origin. A line with slope 0 is forced to be horizontal, so I'm going to draw a tiny horizontal line segment through the origin. Let's try another point for the practice. If I, for example, plug in this location on the y-axis, where x is 0 and y is 1, what happens when I plug that into the ODE? I get 0 minus 1, and I get negative 1. So through this location at 0, 1, I'm going to draw a tiny line segment of slope negative 1. So that's going to have a downward slant at a 45-degree angle. So I've drawn that tiny line segment here at that location. And here, maybe at the point where x is 1 and y is 0, now my y prime is equal to x minus 0 is equal to 1. And therefore, since y prime represents the slope of the tangent line, I'm going to draw a tiny tangent line with slope positive 1 through this location. Now we've only done 3 points so far, and I'm already starting to get bored. So fortunately, we have some technological assistance that we can use to help us to construct slope fields more quickly. So here I am on the Desmos slope field generator. Back in my day, computer-generated slope fields were a lot less nice than this, so I feel like we're a bit spoiled in the modern era. So to get here, I usually just Google or something, slope field generator or Desmos slope field, and it will bring you right here. And in the second box, you can enter the formula corresponding to the value of y prime dy dx in your problem. So in our problem, we have the formula y prime equals x minus y. I'm going to type that into the box, give it a minute to think, and here we are. Here is the slope field corresponding to this ODE. Now we can see some confirmation of the results that we already got by hand. If I zoom in a bit, here at 0, 0, you can see the horizontal line segment that we drew. Here at 1, 0, you can see the line segment with the slope of positive 1. And here at 0, 1, you can see the line segment with a slope of minus 1. Now the tricky thing about slope fields is that they are showing the tangent line segments to all the different possible solutions to the ODE at the same time. In general, even simple ODEs have infinitely many solutions. This is what we saw back in Calculus 2 when we had, for example, an ODE y prime equals 3x plus 4. The solutions had the form y equals 3 over 2 x squared plus 4x plus c, and depending on the value of c, you would get a variety of perfectly valid different solutions. What we're seeing in this slope field are the tangent line segments to all of the different solutions at the same time. So someone says, sketch the graph of a few solutions to the ODE. I'm going to show you how I go about doing that. To sketch my first solution on this graph, I'm going to start by choosing at random one location in this picture. I'm going to randomly just throw a dot into this XY plane. Maybe, for example, that dot ends up here-ish. What I'm going to do is I'm going to try and figure out what the solution passing through this one dot looks like. Now this one dot coincides with this black line segment, which is close to being vertical but has a slight rightward tilt to it. So I'm going to extend my dot into a line that's moving mostly down with a slight tilt to the right. So now looking up above my green point, I'm touching this red line segment, which also has this sharp downward tilt with a slight movement to the right. So I'm just going to follow that trajectory upward until I hit the end of the picture. Likewise, moving downward, I'm going to continue to move down and slightly to the right, following the motion indicated by these tiny line segments. Until now, I begin to encounter tangent line segments, which are not pointing down quite so sharply. The line segments that I'm encountering are beginning to pull upward. So to match that, I'm going to have my curve begin to pull upward, not point down quite so much. Okay, now I'm beginning to encounter line segments like this red one here, which are almost perfectly horizontal. So I'm going to match that by making my curve go horizontal for a little while. But now I'm running into line segments with a slight upward tilt, pointing to the upper right. So to match that, I'm going to have my curve also point to the upper right and follow that trajectory out to the end of the graph. In green, what we have drawn is the graph of just one of the many different solutions to the ODE. The solution that seems to be passing through the particular location at, roughly speaking, -6 on the x-coordinate, +6 on the y-coordinate. So let me make a note of that. Green graph is solution that passes through the location -6, +6. Let's graph another solution curve passing through another point for some additional practice. So maybe I'll pick the location down here, just at random. Suppose that I want this location at 0 on the x-axis, -5 on the y-axis. Now when I'm drawing the graphs of solutions on a slope field, one of the things that helps me to visualize what I'm doing is to think of the slope field as representing the current of flowing water. And I imagine myself dropping a leaf onto the water at the location 0, -5, and I ask myself, how would the current pull this leaf through the water? Now, if the current is moving in the top right direction, the leaf will get pulled up and slightly to the right, up and slightly to the right. And then it looks like it's moving more and more to the right as we increase in height. If the current instead is going to the bottom left, then that leaf is going to get pulled down in this direction. So this red curve would be the graph of a different but also perfectly valid solution to this ODE. This would be the solution which passes through the point 0, -5. So those are slope fields. Slope fields are incredibly tedious to make by hand. We almost never construct them by hand, but nowadays it's very easy to construct a slope field using a computer. And once we have the slope field, it's very easy to, in some sense, just connect the line segments to graph a solution passing through any given starting position. For example, starting at negative 6, 6, or starting at 0, minus 5. Now, just having the graph of the solution and not having the formula for the solution is not optimal, but if it turns out that you are unable to actually find the formula for the solution to the ODE, having the graph at least is better than nothing. So that concludes today's material. We talked about solutions to differential equations, what a solution is, and how to determine if a given function is a solution. Then we introduced slope fields, and we discussed how to graph solutions on slope fields, passing through specified initial points.